Okay.
Everything in this room.
Probably do it
Then
yourself.
the camera fixed.
Okay, now
Why
we'll,
don't you just flip the computer?
Max.
whoops, that's gonna fall off.
I'm just like smart like that.
Okay, I think it's set. I think it's recording. Yes, yes. Okay, section 1.2, that's what we're looking at right now. So get out your notes. Again, you can either continue on the bottom of your notes,
What if I have no room?
then
Then you go
use
back.
a new piece of paper.
Wow.
You can always go in the back.
Okay, guys,
Oh, you just flip it.
Mason.
Okay, guys.
Okay.
Okay, so either start a new piece of paper or continue with what you started at home. Okay, you're going to take some notes now. So section 1.2, the big topic there is describing patterns. We're looking at patterns, and in the world, if we look around our world, there are patterns all over the place. In fact, one pattern that repeats in nature all the time is called the Fibonacci sequence. It's a pattern that you can't really describe algebraically, but you can put it down. And what it is it goes 1, 1, 2, 3, 5, 8. So it takes the first two, adds them together, and that gives me the third. If you take the next two, add them together, that gives you 3. If you take 2 and 3 and add them together, that gives you 5. If you take 3 and 5 and add together, it gives you 8. So you add the previous two terms, and you can see this all over in nature. You go out and look at a pineapple, just the pineapple itself. You will see there's a combination of these numbers, 1, 1, 2, 3, when you're looking at them. Petals are usually one of these numbers. The petals of a flower are usually one of these numbers when you're doing it, okay? When you look at, if you look at a shell that's kind of a nautilus shell, that means it's got that spiral thing there if you look at it, or a snail shell. If you cut that, actually the sizes of the different things represent this. You can measure the different lengths of the spiral, and it actually causes that to be seen. So if you just type in, I'm going to write it, Fibonacci sequence, and you ask for images, like when you're on your computer, if you go Fibonacci sequence, ask for images, it will show you also, and ask for maybe natural images in nature. Okay, because if you put images in nature, then it will show you a whole bunch. If you know what a sunflower is, the arrangement of the sunflower seeds around is in Fibonacci numbers. So if you count the middle and then go to, it just goes around in the same Fibonacci. So it's a really neat sequence or pattern, okay? Now we're talking more about basic patterns in this class right now. Patterns that we can look at where we're adding or multiplying by something, and that's a pattern, okay? So they give you a table of some patterns. So a pattern, okay, they defined a pattern, okay? How do you describe a pattern?
A sequence.
It's kind of like a sequence, okay? We are looking specifically at pattern. So a pattern is, it follows a rule. Okay, the rule up here was take two previous terms, add them together and get the next one. Two previous terms, add them together and get the next one. So you can give the rule of finding the next one. That's really what a pattern is. We follow some sort of rule. Okay, we add 25 each time. We add 5 each time. It's really different rules that we're using, okay? So there are many instances. Instances just means that there's a whole bunch of different numbers you can go through, and it usually can be infinite. Okay, so I don't really care if you know what the word instances means. It's just a different occurrence of it. Okay. So the next thing is we are talking about, so to describe patterns, to describe the patterns, we need to know what a variable is. A variable is going to be defined as a letter, usually a small letter. It can be capitalized, but most of the time we use small letters that represents the instance or where it falls in the pattern. Okay, so it represents where that falls in the pattern. That's really how it is. So a variable is a letter that represents a number, and the number may be different, is different for each instance. So let's say you're doing this. I start with the number 1. I'm not going to do anything to it. So my rule is going to be, well, we're going to add 5 each time. Okay? So here's the first one. 1 is going to be 0. 2 is going to be 2. Yeah, 2 is going to be 5. I did this wrong. I'm going to start with 0, 0. Sorry. 0 is 0 because we didn't add any 5s yet. So at 0, it's 0 because there's no 5s. We're adding 5 each instance. Okay, so at 1, it's 5. At 2, I add 5 to the previous one and I get 10. Does that make sense? At 3, I'm adding, I get 15. So this is your instance for the number in the pattern. This is the answer that you get with the rule, okay, that you're following. Okay. So when we put a variable in, the most common variable we use is what?
X.
X. In algebra, the most common variable we use is X. So why then can't we use the multiplication sign anymore?
Because that's an X.
That's because the multiplication sign is also an X. So we throw the multiplication sign out and we define multiplication to be something different. It's when you have something next to it or a little dot in between. Excuse me. Our multiplication now becomes either 2 times 3 like that, or 2 times 3 like that, okay? Or, now this doesn't work with numbers, but if you have a letter in a variable, you don't even have to write the dot. Because mathematicians are very lazy and they don't want to write any extra stuff they don't have to, so they just drop it. Yes?
Fun fact, in the olden days of math, everyone had to answer a problem, they would have to say in their notes, is equal to every time, so they just, one
Yes.
person just developed
Yes.
equal sign.
Yes, that is true. That is true.
I like fun facts.
Yes, fun facts are fun. I like you to bring those. Those are fun. Okay. So, there are sometimes our patterns are different. So they give you charts here. They're giving you tables. So like for example, 2, an adult ticket costs $15 and a child ticket costs $8. So then you're looking at how much does it cost for 2 adults and 3 children. So really in this case, the price of the ticket is what's the variable. So let's look at this one. I'm going to show you this table that's in there. It's on example 2, which I do recommend you copy the examples and write those down. But this is what our table looks like. We have the family of 2 adults and 3 children.
We should sacrifice all the children.
What?
No.
Where did that
We'll,
just come
we'll get a
from?
better deal. Okay.
Yeah, we can
No.
we can get rid of one, like this one does,
Adult.
and so now everyone has their own room.
You like it? Yeah, it feels weird.
And total price.
Well, if we get rid of
Wait, are those
one of
my
the children.
Okay, wait. Shh. Okay. My inputs over here, we have 2 different inputs. We have adults and we have children. Okay, this is the price. Okay, so this is the number of adults. This is the number of children. We know in this case, they're always 2, 3, 2, 3, 2, 3. Okay? The price is what's changing depending on what you're doing. If you're going to the theaters, the movie tickets are different, the ferry boats are different, and the water parks are different. So the total price is going to change depending on where you're going. So this is movies. This is a ferry. And the last one was a water park. So I'm just going to call it park. Okay? So what is changing each time? Is it the number of adults or children? Is that changing? No, it's not changing. Those are constants. Those are going to be in our pattern. What's changing, Eva? Is it Eva or Ava?
Ava.
Ava. What's changing?
The prices of the places they're going to.
Yes, the thing that's changing with each of these is the price for each of these. Okay? So we can give this a variable. It's changing. So when we're looking at what is changing each time, that's the thing that's the variable. So when you will put a variable for the items, or it can be variables, that change each time. So here, I'm going to call this adult price X, and I'm going to do the children price as Y. So in this case, at the movies, the adult price is $15. I'm just going to write 15 because I don't want to have to write the dollar sign. And I'm going to put $8 for the child. But when you get to the ferry, it changes. So those are the variables. We're changing the variables. Okay. So then it's 22 and 10. And X down here for the water park is 10 and 450. Of course, you're gonna have to change it on me. Put a number in there. There, I can write it small. Okay. So our total price, the way we find that, and this is something we do over and over. Can you tell me what it is we do over and over?
We add, to add the adult children the total price, right?
We want to get the total price. So what are we gonna do over and over?
We should times the price of the children times how many children they are,
Okay.
and then you times the adult as well,
By how many adults there are.
and then you
Okay.
add them all together.
Okay, so it looks like our formula is 2 adults, right? Because that stays constant. In this situation, the 2 adults is staying constant. Times the X variable, which is the cost of an adult price ticket. This is something we use, quantity. We'll use a lot when we're making up things, and this is cost. So we get quantity times cost is always a total cost for something, okay? That will be something we will use over and over and over in algebra, so just kind of get used to that. To the amount, the quantity, times the price is to the total cost for that. Then we have, this is for the adults, now we have the children. There's 3 children in each case, okay? And we have to multiply theirs by the cost of the children's, and we call that Y. So now we have actually a formula that is for, or a pattern. This is our rule The rule is this: we add these two together after we multiply them. Okay, that's our rule. And it tells us what we're going to do. It says we're going to take the cost of the adult ticket and multiply it by 2. We're going to take the cost of the child ticket and multiply it by 3. Add them together. That's our rule for this table. It's explaining it. Okay. And then now it's just a matter of our order of operations and finding the values of X and Y. Okay. So that's what we're looking at. So this is called the rule. We're writing it algebraically. We've defined this as a variable. It changes each time because it may be the same sometimes for adult tickets, but it changes usually every time. Okay, so when we're looking at these, there's different words that we look at. Okay, so anything that's multiplied together like 2x, that is called a term. A term is something that's multiplied or divided. Okay, exponents fall into this also because if you think of exponents, just repeated multiplication. So a term is any number or variable, or numbers and variables, that are multiplied, divided, or have exponents on them, because that's another way of writing multiplication. Okay, so that's just a standard term. So in a term, the number that you have is called the factor of the term. So that's called the factor. I call it the coefficient. So you will hear me call it the coefficient most of the time. I'm going to call it coefficient. You will find that there are multiple words to describe things. Just like in English, we have multiple words or synonyms. There are synonyms in math, so sometimes we use different ones. I will let you know what I'm going to use most of the time, okay, so that we can know that. Okay, let's see. Okay, the next thing is an expression. This whole thing, we kind of talked about that before, but terms added together, so when we add or subtract terms, those are called an expression. The thing an expression does not have, it does not have an equal sign. So an expression does not have an equal sign. Formulas do. And what we generally do in algebra is we actually come up with lots of formulas. That's the whole idea behind algebra is we're generalizing things into formulas so we can use those formulas. And that's what algebra is really figuring out, is what formulas can we use. And so that's the whole idea behind algebra, is that generalization so we can have a pattern or a formula so we don't have to write down every time what we're doing separately. We can say in general, this is what we do, and we can have a rule for it. Okay, and so that's really the important thing. And in life, formulas are what you use. So in your job, you may have a specific formula that you need to use over and over and over again, or several formulas that you have to use over and over and over again. But every time you go to the store, you're really using something like this. Okay, now you have a couple variables in your store. It's the quantity times what the price of the item is. And you may have 17 different items. So you have all sorts of different prices that you add together. Okay, so you take, a lot of times it would be represented this way. Okay, and you can go on and on. Okay, so different coefficients, different prices. So the quantity and the price you use together, and then you add them all up. That's what they do when they're doing your checkout. Okay, they used to do more. Now we scan it a lot of times, every one of them. But you'll still see people scan one of them and then type times how many that you're buying. So if you have 12 of them, they don't want to sit there and scan 12 of them. Okay.
They scan the same thing multiple times.
Yes, they can do that, or they can scan one and just say there's 12 of them that they're buying. It goes much quicker. You have one line on your receipt instead of 10. 12 or 25 or whatever you have, okay? Okay, so, oh, I'm not gonna go into the properties. The property of addition is just saying it doesn't matter what order you add things, they always equal the same. And the commutative property says, of multiplication says, if I multiply two numbers, you can multiply 3 times 4, or you can multiply 4 times 3 and you get the same answer. That's what those properties say. I am not a big deal if you know commutative property. I want you to know that it works. You can multiply in any order, you can add in any order. Okay? So multiplying numbers together, any order you want to do them in, you'll get the same result. Adding numbers together, any order you want to do them in, you'll get the same result. That's what I want you to know. I don't care that you know that's called the commutative property. Okay, because no, you're never going to go up to somebody in life and say, oh, wow, I used the commutative property of addition today. You're just not, and so I want you to know that you can multiply them or add them in, because that actually helps you. Do the simple multiplications first, then do the more difficult ones. And do the simple additions, things that add up to 10, do those first, then do the other ones. You don't have to go in order. You can add them in different orders, and it makes addition a lot easier when you have a lot of things to add up. Okay, so,
Are we gonna use these whiteboards today?
oh, you might, yes. Is that just killing you? You want to?
I feel the urge.
Yeah, the last class put them up, so
Shame on.
this class is the best, or this one is the best done, but it will work. I'm gonna get another one for the fourth window. In here, you get that one. Depends where I assign you. I'm gonna assign you differently. Oh yeah, every day you work with different people.
Wait, what?
And you make.
What?
I thought you said we got to pick our partners. It's
Oh,
like,
yeah.
You can pick your partners one day, and then the other day I'll switch you.
that's fair.
Oh,
Or
okay.
the next day we switch.
Okay, equivalent expressions, okay? So, a sequence, this is defining a sequence. This is 1.3, by the way, so I'm on to 1.3. So if you want to switch in your notes to chapter or section 1.3, you can. Okay, so if you want to pull out 1.3, we are now talking about 1.3. This is all about what's called equivalent expressions. Okay, a sequence is a number with a pattern with a specific order. Like our Fibonacci sequence, you have to keep it in this order. You can't just write numbers down. You have to keep it in this order, or it's not a Fibonacci sequence, okay? So those have specific order. This is the first term, the second term, the third term, the fourth term, etc. in that sequence, okay? So this is where it gets confusing. Remember I talked about terms in an expression? Well, the word term now is being changed. The term is where it falls in the spot in order. Is it the first, second, third, fourth, fifth, sixth in the sequence? So when we're talking about sequences, term is defined as the place an object or a number falls in the sequence. This is an order number, which is usually like first, second, third, etc. Okay, so this is your first term, second term, third term, fourth term, fifth term, sixth term, seventh term. So it's where it falls in the sequence. You just count and see where it falls. Okay, so they're going to be looking at some different sequences. They like to use toothpicks for looking at sides of a rectangle or a square or whatever they're drawing. okay? They use, I'm not sure what they're using, dots, I guess, in one of them. So they're having you look through these, what is the term number, how many are on there, okay? So we'll come back to that, let's see. So sometimes we describe how we would make that pattern, because there's a pattern usually to a sequence. Okay, so let's say we have the sequence. Let me see what one we have here. Let's do the toothpick one. So everybody turn to page 20 so you can follow along. Page 20. We're looking at the toothpick sequence. Okay, on that page. Do you see it? Okay. So term 1, how many toothpicks are there?
4.
4. How many So term 1 has 4. Term 2 has how many toothpicks?
7.
Okay, so term 2 has 7.
Well, if I did not.
Term 3 has many. How many?
10.
10. Term 4 has how many?
13.
Okay, 13. Look at this. Can you see a pattern? What pattern do you see that we're doing? Yes.
You add 3 every time.
We add 3 every time. Okay. Oops, between those is 3. So I always like to see, this is my pattern. Okay. So I've added 3. That means we're going to do something with 3. Okay. What did we start with? This one is not 0. What did we start with? 4. We started with 4. Okay. That means it's going to be my starting number. Now, this is a little bit interesting, okay? On term 1, obviously the number that you're in the pattern, this is my variable. Now, it doesn't matter if you call it X or N, as they call it. N is standing for the number in the sequence. Remember, it's the term, the number in the sequence. So that's, N can stand for that, X can stand for that. It doesn't matter what variable you call it, okay? But that's the thing that's changing, so it's the variable. We started at 4, and then we added 3. So it looks like we take our number, and we add 3 to it, okay? Our term before, and we add 3 to it. But this is 1. Actually, this isn't right. I screwed it up. What are we, sorry.
Is it multiple?
So we're actually, what are we doing each time? We're adding 3 each time, which is multiplication, right? Multiplication is repeated addition.
Oh, yes.
Because if I do 3 plus 3 plus 3, that is 9, which is the same as 3 times 3, right? So if I'm in the second one, we're going to add 1, 3. Okay, so that is interesting. We know we're adding 3, but is it 3 times the term, or is it 3 times 1 less the term? How many 3's did I add here? To get the second term, how many 3's did I add?
1.
1. So we use n minus 1 because you're only adding 1 3 because that's the first one. Okay, now what did we start with? Well, we started with a 4, right? Is that correct? So that's what we're going to add. So we're adding 3 for every time that the number goes up 1. Okay, now if it's term 1, how many 3's do I add?
None.
I would take 1 minus 1, what does that give me?
0.
0. 3 times 0, I'm not adding any 3's for the first term. That's how we can double check it. Do you understand that? Let's look at this. So if my term, we're going to see if our pattern, this is what we're describing our rule at. Okay, we're describing our rule. When you see the repeated multiplication, or repeated addition, that's multiplication. Okay. When you see a number that it starts with, usually we put that number first. Okay, and we add to that. So let's see what we get. If I'm doing term 3, it says I'm going to start with 4. I'm going to add 3, and then my term is n or x. I'm going to do 3 minus 1, 4 plus 3 times 2, because 3 minus 1 is 2. 4 plus 6. That equals 10. Does that give me what I counted over there? Does that give me what we originally counted off the
C.
diagram? Yes. So that is our rule for finding the variables. Okay, so it takes a little practice. I'm just letting you know, in a sequence, we usually use n minus 1 on all sequences. Not always, but a lot of times. Okay, so that's something to look at. Okay, so now, somebody might say, he does it differently. Maybe, so somebody came up with this one, we'd say, okay? Somebody said, I don't like using that, so I'm gonna say, I'm gonna start with 4. No, I don't wanna do that, okay? Because that'll give you the same thing. We're gonna start by taking, I can't think of a different way of saying this, I gotta think.
1 plus 3n.
3 times n, wouldn't be plus 1. Three times that plus 1, does that work? Oh, it does. Okay, you're right, thank you. So somebody else figured out that that pattern can be described like this. They said if you take the number of the variable, or the term, multiply it by 3 and add 1, you'll get the same result. Let's check. 3 times 1 plus 1 equals 4. So when it's 1, the first term should be 4. Ah, it is. Okay, let's check the second term. 3 times 2 plus 1 should be our second number of toothpicks. 3 times 2 is 6 plus 1 equals 7. Look at that. 2 is 7. Okay? Both of these are ways to describe this pattern. Okay, so that is one way of doing it, describing it in a different way. Okay. Now, what we're talking about equivalent expressions, it's when two things give you the same thing. So this expression here, this rule here, is actually equivalent to this one because no matter what term I put in, what number I put in, I'm going to get the same answer. So equivalent means they give you the same answer for the same term. Equivalent means same. So you get an answer, same answer for each term. Okay, so no matter what I put in, both of those will give me the same. So one way to check if equations or expressions are equivalent is check to see if they both equal the same thing when you put in the same number. Okay, so let's check one. We're going to check one. They gave us here, let's say, this is our expression. We have k minus 8 plus 5 and k minus 13. These are the two expressions that these guys came up with. Okay, so we're trying to see if they're equivalent or not. So one guy, and this is something you guys can do, even when you're working on these, you may get different answers. But we're checking to see if they're equivalent. So we have, I can't remember what it was, minus 8 plus 5. K minus 8 plus 5 is one expression. The other expression is k minus 13. Okay, we're asking, are these two equivalent? So what you do is you put numbers in for K and see if you get the same thing. So do 1, 2, and 3. Do about 3 instances to see. Because I'll tell you, if you put 0 in, sometimes you will get the same answer, and sometimes when you put 1 in, you'll still get the same answer, but it doesn't mean it works for every case. So you should check a few cases to make sure. So if I put 1 in for K, I get 1 minus 8 plus 5. If I do that work, I get minus 7 plus 5, I get negative 2. Does everybody agree with me on that? Follow what I did? 1 minus 8 is negative 7 plus 5 is negative 2. Another way to do this is add 1 and 5. They're both positive. That gives me 6. 6 from negative 8 is also negative 2. Sometimes I put all my positives together and then subtract it from my negatives. Or vice versa, depending on which one's positive, which one's negative. Okay? Over here, it's going to be 1 minus 13 is minus 12, right? Because 1 minus 13 is negative 12. Right now, without doing 2 and 3, are these equivalent? No. Not the same answer. So, not equivalent. So, when you're making up formulas, you need to make sure it works for every answer. That's basically what this is telling us. But we're going to talk about equivalent expressions as we go through this more and more. Okay? So, I used one. They use different numbers. They use 10 in there for this instead, but it also shows you that they aren't the same. Okay? So, we have an hour. We have just covered this. Now what I'm going to do is, let's see, you're going to have a hard time. You want to just work at your desk?
I'm gonna have the hardest time.
I'd like to work with other people, but I mean, I can move to this.
Why don't you do that? Yeah, if you can move down one chair, then I'll put a couple people with you, and then we can work on that. You can work with them, okay? So we are going to start with 3 people, 3, 2, 2 is what I think I'm doing.
So it'll be
Yeah, works. Okay, so Mason and Grayson, you're working with Matthew. Do you go with Matt or Matthew?
Matthew.
Okay, Matthew, you're working with him at this board? Oh boy, this will be interesting.
No, we'll do good.
Okay,
I doubt that.
When we actually want to focus, we can focus.
I don't believe
so
it.
you guys are up on the second board,
Okay.
okay, and you guys are on the third board. Now, there is no
That's a good.
marker there,
I got us one.
okay?
I'm just gonna look at it.
Nuh-uh.
Oh my gosh, I can barely stand up right now.
We are gonna use paper towels and water to wash these.
No, it wasn't that. Did you run a half marathon this weekend?
No. But I did football. I had to choose out some food.
Okay.
Alright, let's see.
See this, I just finished my notes for.
Wait, you don't even know what you're doing.
What are you writing?
Is that yours?
Yeah.
Okay, do you guys have a pen? Mason, you have one, okay.
Wait, so is it you and me
I'm trying to
next?
move it over to the.
Yeah, that's good,
Is it
okay.
just me next?
Yes, you are, just together.
Okay.
My gosh, you
That's why I
grew
said
a
we
lot.
can lock in when we want to. Oh, uh-oh.
Okay.
Will that stain?
Wait.
Oh, I just played.
No, well,
Okay.
it shouldn't.
Okay.
It's erasable, so water should take it out.
So I can use this as an eraser.
Well, we're gonna use paper towels, so don't write extra that you need to erase. So I will give you a set of paper towels. When we go to clean it off at the end, we're gonna use water, so you'll come and bring your paper towel up and get water on it. Hey. Don't get distracted. I know it's easy. Don't get distracted. Okay, somebody needs a book in your group, so grab a book.
I can use Red's book.
Get one book. It doesn't matter which one.
Wait, let's see. Is there one anyone?
Oh, we also have it right here. Just me. How are we gonna? I had a judge.
Oh, yeah.